This is the design problem that we gave a go in class. And we're going to go through the design steps and design an amplifier that meets the specifications. So first of all is clarify the specifications. So for this problem, we looked at Rn greater than 90K, an Rout less than 50 ohms, a Vin at rest of 3 volts, and a supply voltage of 5 volts. And the transistors that we will use are these MPS 650s, which just happen to be BJTs. So those are your specs that you might get from your boss. The next step is to figure out if you're using MOSFETs or BJTs or BJTs. And since I told you in the specs that it's BJTs, we already have an answer for that. I call this the technology. And technology is actually more than just deciding whether it's MOSFETs or BJTs. Technology is the model file. So as you know, if you use a different transistor, you use a different model file. And the model file describes how your transistor behaves when you simulate. So the technology is actually, the values in the model file. Maybe a higher early voltage or a larger, smaller beta, something like that. The technology actually takes all of that into account. But generally in this class, I'll give you the models and just one of the decisions you may have to make are MOSFETs or BJT. Okay, 3 is the topology. And we haven't summarized in class, but on the homework, you looked at the 3 flavors of, or the 3 types of single transistor amplifiers. And that's common source or common emitter, common base or common gate, common collector, and common drain. So those are the 3 single transistor amplifier styles. And you have to pick one of those now that meet your specifications. So in the specifications, I see a really high Rn and a really low Rout. And if you go back and look at that table, again, we haven't summarized in class, but if you go back and look at that table, you'll see that the only amplifier that has a high Rn and a low Rout is a common collector. And again, this has lots of names, so this emitter follower is the same thing. A impedance transformer is another name. And a level shifter is another name. So all of these, and there's actually more names. I'll stop here. All of those are different names for the common collector. These are all equal. So equals. So that's the only topology. That's the only style of single transistor amplifier that has a high Rn and low Rout. So now we've got our topology, and actually running out of space. Okay, so now we've got topology. So next thing is to find equations. And you say, okay, what do we find the pen stopped working again. Oh, that came right back. The equations that you want to find are for things that were given in the specifications. So in the specifications, they gave you Rn and Rout. Vin is a voltage, V supply is a voltage, transistor type, that's the transistor type. But this Rout and R signal values. And so you need equations for them. I gave you the equation for Rn. And you may have seen that in lab already. But it looks like that. For Rout, we don't have an equation for that. So we need to do small signal analysis to find the equation for Rout. So let's do that. Next step is to, so I know my common collector looks like this. Call that RE. This is V in. And notice that the output is at the emitter, not at the collector like a common emitter. First step for small signal analysis is to replace the transistor with the small signal model. It's the same circuit, it just has the transistor replaced with the small signal model. And then so that's just the transistor. And if you notice that the collector, this corresponds to the collector, emitter, base. So this voltage right here is VBE. This is V in. This is V out at the emitter. Then we also have the simplifications. The supply goes to ground. It's a DC source, so it goes to ground. And then you have RE also going to ground. Okay, so you can, so this is, you can clean this up a little bit by putting RE in parallel with RO, but just to save a touch of drawing in time, I'm going to add in the, since we're trying to find R out, I can do this. Actually, since cut and paste is here, we can rearrange this and put this as and get rid of this here. That's just a little bit of a cleanup. Okay, so now here we have small signal model slightly cleaned up by putting the resistors in parallel. And then, since we're trying to find R out, so R out, what you're looking for is V out over I test. So I out is current out of your circuit, but I test, since you're trying to find the resistance, usually you put current into the resistor to see what resistance it sees. So I test is actually negative I out. And then you get to use a two-port simplification here, which is V in equals 0. So if you do that, then that, and get rid of this. Okay, so now you have this, and since to use the two-port rule, we'll use this purple, maybe. And stop working yet again. Okay, pen's gone, pen's not working. Get to ground this. Okay. So our VBE goes from this node to this node, and this node is now 0. This node is V out. So VBE okay. So that's the first thing to notice. And I don't see any 0 volts across resistors, and VBE is not 0 anymore. It's not 0 because V out is not 0. One simplification that I have here is, let's look at the voltage from here to here. So this node is 0, and this node is V out. So the voltage across this current source is 0 minus V out, and So the voltage across the current source is negative V out. Whoops. Darn this pen. Is negative V out. And hey, that equals the voltage inside the current source. So this current source right here, because the voltage across the current source is equal to VBE, can be reduced to a resistor of size 1 over GM. So you now have a non-working pen yet again. So you have R pi, you have 1 over GM, you have RO parallel RE, and this is V out. Sorry. I saw it move for a sec. Okay, pen's dead officially. V out right here, and this is also grounded. And what you do if you put current into here, what you see is a resistor. All of these resistors are going from this node to ground, so all of these end up in parallel. So your R out, which equals V out over I test, just looks like a resistor of all of these in parallel, which is R pi parallel with R, V parallel RO parallel 1 over GM. Okay. R pi is very often something like 10K. RO is very often something like 100K. RE ideally is large, and for this problem it actually comes out pretty small, but if you approximate it as 1K, then all of these are over a kilo ohm. But GM is often, not always, but often, GM is often is somewhere between there. So 1 over GM is often is greater than 10 to 100. So if you're going to put a 10 ohm resistor in parallel with these, what happens is your R out is approximately 1 over GM. Okay, you can leave all of these in and calculate it out, but again, our current equation where we've derived the equations for R pi and RO and GM, that current equation is already simplified. You've already got some error there. So these equations are to get ballpark. It's pretty close, but it's not going to be exact. So if you did this all out, you might get a little closer to the actual value, but it's not worth the time over using 1 over GM for your equation. Okay, so now we have our equations. So we know that this is the R out spec. 1 over GM is the output, and that has to be less than 50 ohms. So let's work with that for a second. We know GM is IC over VT, so VT over IC needs to be less than 50 ohms. And for VT, if you use 25 or 26, it's all good. IC has to be less than 50 ohms. So your IC your IC, do it this way, IC has to be less than 25.9 millivolts over 50 ohms, and that actually comes out to, what did I get, 0.5, 0.5, 52 maybe. Okay, yeah, something like this, milliamps. So as long as IC is greater than that, you'll satisfy the R out value. Okay. Then you have the R in, which is R pi plus RE 1 plus beta, and that has to be greater than 90K. And you know R pi, you have an equation for R pi that you found by taking the derivative of the current equation. That's beta VT over IC. And then you're trying to find RE. And then from the model file, you have, I think it's 192.66 for the beta. And that has to be greater than 90K. So if you work this, yeah, so now we've got two equations. We've got one equation for IC. IC has to be greater than 0.52 milliamps. And then you've got, if you plug all these numbers in, beta from the model file is 192.66. And then VT, again, 25 or 26 millivolts. So you have an equation here with two unknowns, IC and RE. You have some information about IC, that it needs to be greater than 0.52 milliamps. And I think on the data sheet, I have to go look this up, I'm sorry, but I think this transistor is happier with like a milliamp or above. So I am just going to pick 1 milliamp for this. And you could have picked a different current. That would still be, there's an infinite number of solutions to this problem, but I'm just going to pick IC equals 1 milliamp. So if I use IC equals 1 milliamp and then solve for RE, what I get is RE, do here, RE is, so if I pick for 1 milliamp, whoops, I've missed all of that, but I think I got, needs to be greater than 425 ohms. Okay. And so now we have a current and a resistor. RE needs to be greater, yes. RE needs to be greater than that. So now there's one final check that you need to do. I gave you that Vn equals 3 volts. And all we know right now, we're designing for 1 milliamp, but all we know is RE is greater than this. What you have to do here is to guarantee that you have 1 milliamp going through here. You can find out what V out is. So V out is always V in, approximately, V in minus VBE on. And you can find VBE on from the model file, and it's 0.77891. And so that, what does that give you? That gives you, since Vn is 3 volts, that gives you 2.22109 volts. So that's the voltage across RE, and you need to get 1 milliamp. So what does RE need to be? You have 2.22109. That's the voltage across it. You have 1 milliamp. So you multiply this by 1,000? Really, you need that big a resistor. Whoops. 2, 2, 1 ohms. And now, so now you'll get your 1 milliamp when you're at rest here for this RE, set RE. And now if you go back up to our approximation we did up here, this RE was actually 2K. And so this actually, your 1 over GM, your 50 ohms in parallel with any of these just dominates, and the 1 over GM was a good approximation. And that's how you design from specs to design.